Good day. My name is Sean Augenstein, and I work at Google Research on federated learning and other tools for privacy-preserving mobile intelligence. I'd like to share some recent work by myself and several colleagues on uses for generative models in federated computation scenarios. Federated learning, or FL, is a technology for training models when data resides on users' edge devices like mobile phones. For a lighthearted refresher on FL, I recommend checking out federated.withgoogle.com. A particular challenge for the FL modeler: you can't directly inspect the data set. You and your model reside at a central server, like this cloud depicted at the left, but the user private data that you're training on resides in caches on the edge devices depicted in the circles at the right. So how do you inspect the data? And I would submit that data inspection is something that all data scientists and ML practitioners do. Contra this tweet, which I do find very amusing, it isn't crazy to inspect data. Not at all. You're not a psychopath. In fact, we came up with a table capturing just a handful of the many tasks for which a model developer will, in the course of performing machine learning to train a model or evaluate a model, need to inspect data and the selection criteria they use for each. So we all do and need to do data inspection. How do we do it in the FL scenario? We propose the use of federated generative models. The idea being, can you train a model that synthesizes novel examples that match distribution with a broader decentralized data set? An important detail here: privacy is absolutely paramount. The entire motivation for FL is to protect users' private data. If a generative model learned to memorize data that was unique to an individual from their own private cache on their device, that would completely defeat the motivation for federated learning in the first place. So to achieve privacy, we leverage user-level differential privacy. Time is limited, so I refer you to the paper for the details on how we apply user-level differential privacy in conjunction with FL and how we achieved good epsilon delta bounds. Okay, let's walk through an example. Imagine an on-device image model used for inference. Maybe it reads characters in a mobile banking app, some say to do something like cash checks. This model expects, i.e. it's trained on, images with white characters on a black background, like what's depicted here on the right. Now imagine that, unbeknownst to the development team, an app update contains a bug which results in raw image data being altered. Where the images presented to the on-device image model for classification are normally expected to be white characters on a black background, now, on some devices, i.e. the updated devices, there will be instead black characters on a white background. While these images are never directly viewed, and this is never directly realized, because of this mismatch, the classification performance of the on-device image classifier plummets on the updated devices. So how can the development team diagnose what's going wrong? Well, they can train, via federated learning, a generative model on the devices exhibiting low classification accuracy. And in parallel, they can train a second generative model, also via FL, on the devices that continue to classify well. GANs are a natural choice in this case, as we're in the image domain, so we'll refer to GANs moving forward. Okay, so after many rounds of federated computation rounds, which is the basic unit of computation in federated learning, each GAN is converged, and the generators can be used to synthesize novel examples of the data residing on devices in the respective populations. That is, the population of devices exhibiting low classification accuracy, which should be mapping to the devices that have been updated, and the set of devices which continues to maintain high classification accuracy. This difference in images, this black-white switch, becomes apparent by synthesizing these images, and the development team now has a key insight on identifying what needs fixing. That is the basic idea. There's a lot more to the story: how to train with user-level differential privacy, some experiments we ran in different domains with different styles of generative models. Some of the real experimental results from GANs in the image domain are shown here at left. I refer you to the paper for more. One more thing is this work also contributes a formulation of a differentially private federated GAN that's novel, and which we open sourced an implementation of via the TensorFlow federated library at the link shown. In closing, we feel there's a lot of interesting directions to go with the concept of federated generative models. We enumerate a handful of the ideas in an appendix in the paper, but we're very excited to see lots more work in this area at the confluence of federated learning, differential privacy, and generative models. Thank you so much.